Hello and welcome to our talk on MPI CorrBench towards an MPI Correctness benchmark suite. My name is JP Lair and I am joined by my colleague Tim Yama for this presentation. You can also follow me on Twitter to receive updates about our various projects. Now, in this presentation, we present to you our approach to a structured benchmark suite to test, evaluate, and systematically compare existing MPI correctness tools. We also want to foster and support the development of new MPI correctness analysis tools. MPI is the de facto standard for distributed memory computing in high-performance computing. However, MPI is also a low-level interface for which developers need to specify many details. This is error-prone, particularly for large-scale applications. Hence, tool support for correctness checking is desired. Many different approaches to MPI correctness have been proposed. Some are available as actual tools for the end user. The tool capabilities are typically shown on either handcrafted benchmark suites that vary from paper to paper or on well-known mini-apps, which tend to be well-tested and error-free. We address this issue for a lack of comparability between these tools with MPI CorrBench. Hence, we aim to provide a systematic benchmark suite to evaluate the different approaches with respect to their capabilities to deal with different MPI errors. We approach this by inspecting the MPI standard to identify different error categories that we see as fundamental to MPI CorrBench. In general, two fundamental approaches to program analysis are distinguished: static and dynamic. Static analysis does not require the execution of a target program, which can be helpful in some occasions. It typically uses an abstract representation of a state in the program, or may completely ignore state, leading to less powerful analysis. However, due to memory demand, most systems limit the number of states the analyzer can create. Given that it doesn't execute the target program, it can inspect all possible paths through the program during its analysis. Dynamic analysis, on the other hand, requires the execution of the target program. This means that it can actually inspect the real state of the application, for example, all memory allocations. However, it is input sensitive. This means that only those paths can be analyzed that are actually executed during the program run. So both techniques have strengths and weaknesses, and for an overview of the proposed methods, we refer to our paper. The images at the bottom of the slide give an example for, on the left, the Clang Tidy static analyzer, which inspects the program's source code at the compiler level to issue warnings to a programmer. On the right, we see the typical architecture of a dynamic analysis tool, which intercepts the MPI calls at runtime to perform analyses. Now, after the motivation and some background about the different analysis approaches, let us now start with introducing MPI CorrBench. We first show and explain the different error categories that we distilled from the MPI standard. Thereafter, we are going to explain MPI CorrBench's layered architecture with the different levels of complexity. The first error category are erroneous arguments. These are local to one MPI function call. In the example, the number of elements to receive is given by variable x, while the allocation is performed using variable n. Now, should x be larger than n, MPI receive writes outside the allocated memory. This leads to memory corruption and may be a hard crash, or even a silent error, which may be worse. The second category are mismatching arguments. These errors occur when arguments between two matching MPI function calls mismatch. In the example, the data type specification for the underlying buffer does not match across the MPI calls. Please note that the data type is specified correctly within each MPI call, and hence no erroneous argument error exists in the example. Finally, the third error category is called erroneous program flow. It combines misplaced MPI calls as well as completely absent MPI calls. The example shows a misplaced call where MPI wait is placed behind a send buffer modifying loop. Instead, it should be placed before the buffer modifying loop. To systematically approach the implementation of MPI CorrBench, we have created a layered architecture. The slide shows the levels within this architecture. The x-axis denotes the complexity within MPI and its usages, meaning that we have MPI only with its different parts of the API specification, and then going towards more complexity, for example, MPI plus X. The y-axis denotes the technical complexity, for example, being able to handle multiple translation units in an analysis tool. Level 0 contains unit test-like small-scale, single-file MPI applications that provoke single and individual errors each. Level 1 is similar to level 0, but now allows for multiple files per test case. This is to aid the developers in research tools to have a possibility and compare different research tools in different stages of development. Level 2 contains mini-apps, meaning that a tool needs multi-file capability, but also allows to evaluate the runtime impact of a tool. Finally, level 3 is reserved for full applications. This is meant to be able to evaluate if a correctness tool can be actually applied to a fully fledged application and run on production code in production environments. In addition to erroneous test cases, MPI CorrBench includes correct test cases. We have taken them from the MPitch2 test suite, with the idea to trigger potentially false positives in the analysis tools. This table summarizes the different test cases that are currently present in MPI CorrBench for the different MPI features and the different error categories. We will now move on to the evaluation, which is presented by my colleague Tim.
I am Tim, and I want to present the evaluation insights that we gained when we use MPI CorrBench in order to evaluate 4 different MPI correctness tools. We use MUST and the Intel Trace Analyzer and Collector as 2 dynamic tools that execute the application and then collect information at runtime, as well as MPI Checker, included in Clang Tidy, and ParCoach as 2 static analysis tools that do not rely on the execution of the application. Here you see an overview on how the tools performed on the test cases given by MPI CorrBench. In this case, a true negative means that the tool concluded that no error was present, and no error was present in the given example. Therefore, true positive means that the tool successfully detected an error. We did not encounter the case that any tool detects a different error than the error that was supposed to be in the given test case. Warning means that the tool issued a warning about suspicious behavior. The static tools do not differentiate between warning and error though. False negative and false positive are then the occasions when the tool's conclusion was incorrect. Every time we could not interpret the output of the tool, we marked this as a crash. So let's have a more detailed look and start with the point-to-point communication. In this case, we find that ITAG and MUST are mostly complementary, meaning that ITAG finds some errors that MUST misses and the other way around. In particular, MUST misses some errors with non-blocking communication, while ITAG misses some type mismatches. The crashes often result from the MPI library aborting. For example, when a function was called before MPI init, then the tools do not produce useful output. In some test cases, we encountered a segmentation fault in ITAG though. For the static analysis tools, MPI Checker finds mostly misuse of types and missing MPI wait calls. As ParCoach is solely developed for collective operations, we did not expect it to perform well in point-to-point communication. For the collective operations, we find that both must and ITAC miss mostly buffer type mismatches. For ParCoach, we find that it detects the majority of deadlock cases, but not all of them. For example, mismatching root processes are missed. MPI Checker, however, could not compete against ParCoach for deadlock detection. It rather finds some type buffer related issues. ParCoach could not evaluate all examples, and not all MPI operations are supported yet. If an unknown function is encountered, ParCoach aborts, and all the crashes seen in this evaluation results from this fact. For derived data type, we find that must and ITAC are quite comparable in this case. Both misses roughly the same errors. Examples are the creation of a struct type that do not match the underlying C struct's definition. The static tools have no support for derived data types. For one-sided communication, we see that must do not support this operation. False positives mostly originated from that. An example would be that must could not detect that an MPI request object originated from a remote direct memory access call. We see that ITAC also performs significantly worse than for the other categories. It can detect some errors, mostly invalid arguments such as null pointers, but we see that for one-sided MPI communication there is still room for improvement. In our opinion, most of the false positives are actually justified. We use the MPI CH test suite for the correct examples, and of course the test suite has to test some technical legal edge cases, for example zero-sized messages. But if the tools issue a warning or an error in those special edge cases, we did not find this harmful. In addition, the MPI CH test suites includes behavior that is discouraged by the MPI standard. You find several times that several incoming messages are received into the same receive buffer with non-blocking communication operations. And therefore, it's very likely that the receive buffer will get corrupted. As the receive buffer is then not used afterwards, this is no problem in the test suite, but the MPI standard clearly states that you should not do this. And therefore, if this is flagged as a warning or an error by the tools, we think that the tools are right with this behavior. We find that must is more stricter in the case that suspicious behavior is more often flagged as an error instead of a warning. Of course, the discussion what should be an error and what should be a warning is highly subjective. We found in our subjective evaluation of the error messages given by the tools that must sometimes point out the root cause of an error more directly. An example would be that ITAC point out that there is a deadlock with one process hanging in MPI finalize and the other process in an MPI receive, which is the symptom of the error, and must more directly points out the origin of the error, pointing to the wrong receive and send operation. In order to ease the evaluation, we implemented a GitHub continuous integration pipeline that automatically evaluates the tool for each update of MPI CorrBench. Let me quickly demonstrate it. Here you see our GitHub repository. We built a continuous integration pipeline that automatically uses the tools on each level 0 test case. By the way, the long execution time of must comes from oversubscription, as a GitHub runner only have 2 CPU cores available and must needs 3 MPI processes. So this CI pipeline executes all the tools for all the level 0 test cases and then generates the visualization. And then the visualization is automatically pushed to the CorrBench dashboard linked in the README. For this visualization, you see here, we use newer versions of the tools, so this visualization might slightly differ from the ones you see in our paper. In the future, the extension of MPI CorrBench to include more elaborate MPI features, also some new MPI 4.0 features such as partition communications, is planned. In terms of the technical complexity, we also want to challenge the tools with basic and more elaborate multi-file test cases as well as MPI plus X test cases. As Fortran is widely used in HPC, we also want to include Fortran test cases in MPI CorrBench. And of course, we also want to incorporate the evaluation of other MPI correctness tools, such as SimGrid, into MPI CorrBench. We want to develop MPI CorrBench as a community effort and welcome your contribution to extend its coverage. So in summary, MPI CorrBench allows for systematic evaluation of different MPI correctness tools. Our layered architecture allows to use CorrBench with different tools and provide a fair comparison for early stage research tools. So please check out our code on GitHub and feel invited to contribute to further extend the coverage of MPI CorrBench. And with this invitation to check out our GitHub, we want to thank you for your attention and are looking forward to the following discussion.